Hello, welcome to the SeqSMART, where genomics meets the future. In this video, I will introduce the SeqSMART Sanger Viewer, a tool designed for analyzing, reviewing, and interpreting Sanger sequencing data. The access link is provided below this video. To begin, simply upload your AB1 file in this section. After a few seconds, the file is loaded and the sequence view is displayed. Here, the first track shows the reference sequence. The second track is your uploaded sequence and you can see raw chromatograms here. And the third track displays the expected sequence. You can use the zoom tool to focus on specific regions. The trim option allows you to remove nucleotides from the beginning or end. You can also navigate along the trace and inspect the chromatogram. Detected variants are listed at the bottom. For each variant, gene annotation and a genomic region viewer are available. This view shows whether the variant has been reported in ClinVar, and which other variants exist in the same region. By clicking this button, you can jump directly to the variant position. You can delete or hide the variant, add a new variant, or modify the zygosity. If we click on the variant itself, we are taken to the variant analysis page. On this page, all 28 ACMG criteria are available. For this variant, the PVS1, PM2, and PP3 criteria have been met, and based on these criteria, our prediction is that this variant is pathogenic. Now, if we want to understand why PVS1 has been met, we can view its details in this section. As you can see, this variant falls into the loss of function category, is classified as a stop-gain variant, and due to the activation of nonsense-mediated decay, the PVS1 criterion has been applied. You can click on each of these criteria to change its strength, view more detailed information, or check the variant frequency in the population. You can also see the most common non-pathogenic variants in this region. At the bottom of the page, more detailed explanations are provided, showing why each criterion is considered met or not met for this variant, allowing you to review them in detail. In the variant details section, the familiar genomic region viewer and ClinVar information are once again available. You can also see the allele frequency table, where in this example, the frequency of this variant is reported as 0. In this section, computationally generated predictions are also displayed, including conservation scores, evaluation of the variant's impact on splice sites, CADD score, and the results from prediction tools such as SIFT, Mutation Taster, Polyphen and other predictive algorithms. In addition, the gene transcript structure is visualized graphically in this area. In the references section, you can view scientific publications related to this variant. This page loads after a few seconds, and you can directly navigate to the corresponding PubMed page for each article from within the system. Similarly, in the associated conditions section, diseases linked to this variant are displayed. In this example, the variant is associated with keratosis and erythroderma. By opening each condition, you can view the associated HPO codes and review the reported phenotypes for that disease. Finally, at the gene details section, you can explore comprehensive information about the gene, its structures, protein-protein interactions, 3D structure where available and other relevant information. I now load another example. For instance, I upload a file related to the HBB gene, or beta thalassemia. In this section, we have 3 variants. If we click on the first variant, it appears here. Let me zoom in a little so it is easier to see. Once we click on it, we can see that the variant is located at this position. In the same way, we can view the next variant. As you can see in this image, the variant is located in this region. Normally, we would expect an A at this position, but instead, there is an A to C mutation in this region. There is also another variant located here. I intentionally selected a low-quality file for this example, so you can see that even low-quality files can still be analyzed. And if we click on this, we can see that this variant is benign. In fact, it corresponds to histidine at position 3 in this gene, and a population frequency of 82.6% has been reported for this variant. If we go to the variant details section, you can see the spectrum of mutations reported in the beta thalassemia gene at this position. As shown here, this variant has been reported 18 times as benign. You can also view the frequencies and frequency tables in this section. In addition, you can see the ClinVar submissions, as well as the prediction results. As shown in the image, this region is not highly conserved, and one of the predictors has classified this variant as non-pathogenic. The transcript structures are also displayed here. From here, there is no need to go back or click elsewhere. You can directly navigate to the next variants from the top, and as you can see, all 3 variants in this gene are classified as benign. I now load another file for you, which again contains an insertion. One additional feature we provide is the indel detector. When your file contains an insertion or a deletion, you see this typical pattern. Up to the indel position, everything looks normal, but from that point onward, the chromatograms become disrupted, and this disruption continues to the end of the graph. This pattern is a clear indication of the presence of an insertion or deletion. Our indel detector can use the reference genome to separate this disrupted chromatogram into 2 distinct traces and identify exactly where the insertion or deletion has occurred. As you can see here, there is a G insertion, and if we click on it, it is reported as likely pathogenic. The disease associated with this variant is autosomal recessive deafness 28, and you can also view the clinical features. If we now go to the gene details section, the interaction network and all related information for this gene are available and can be explored. As another example, if we select a low-quality file and take a look at its structure before uploading it, we can see that the quality is not adequate. When we upload this file, an error message is displayed indicating that the file cannot be read, most likely because it does not correspond to human sequences. Therefore, it is important to use files with sufficient quality. Next, I will show you another deletion example and upload a file with bad quality. As you can see, even in a bad quality file, we can still identify insertions, deletions, and variants. This one appears to be a real variant, while this one seems to be noise. If you are confident that a variant is noise, you can simply click here to remove it. And it will be immediately deleted from the list of variants below. As you can see, this variant is real, and this one is most likely noise. I can easily remove the noise, and it disappears from the list. This allows me to review the consequences and outcomes for each variant separately. On this page, our indel detector once again identifies a deletion in this file. We can navigate to that region and see the deletion here, which in this case is noise caused by the poor file quality. However, if If we select a file with appropriate quality, we can see that the indel detector correctly identifies the variant again. This is a 2-nucleotide deletion, specifically an AG deletion, and its result is classified as likely pathogenic. This variant is associated with beta thalassemia. Thank you for watching. We hope SeqSMART helps you analyze genomic data with confidence.